Hi, my name is Sanjoy Kundu. I am a PhD student in the Computer Science Department at Oklahoma State University. In this video, I'll be presenting our paper, Iterative Scene Graph Generation with Generative Transformers. The conventional approaches consider all the pairwise relationships within all the detected objects. They do not reason over the underlying semantic structure. Instead of starting with a fully connected graph and pruning edges, we first sample the graph. We find the edges between the objects that might have a meaningful relationship. At first, we ground the concept of an input image using a first error in an object detector. In the second step, we perform structural reasoning over the nodes and sample the graph by a generative graph transformer. We input this sampled graph to the third step of our approach, relational reasoning, and then generate the graph. We evaluate our approach on the visual genome dataset. Hi, my name is Sanjoy Kundu. I am a PhD student in the Computer Science Department at Oklahoma State University. In this video, I'll be presenting our paper, Iterative Scene Graph Generation with Generative Transformers. Conventional approaches start with a fully connected graph by considering all the pairwise relationships between detected objects. They do not reason over the underlying semantic structure. For example, given an input image, we get object labels and bounding boxes using an object detector. In a conventional approach, the edge construction is performed using a permutation between all the objects except for the cell group. Then a relation prediction model predicts the labels for the edges, including a background class, to generate the final scene graph. Instead of pruning a fully connected graph, we begin by sampling the underlying graph structure. We try to find the edges between objects that might have a meaningful relationship and discard the edges that are not likely to have one. For example, in this image, we have grass and trees as objects, and there is no relationship between them that can help to understand the scene. So in our graph sampling approach, we try to discard these edges before going to the relation prediction model. On the other hand, the entities man and frisbee might have a semantically meaningful relationship between them. So we want this edge in our sample graph. Once we have the sample graph, we predict the labels of the edges using a transformer-based relational reasoning model. Conventional approaches ignore the underlying semantic structure during relational reasoning and model the interactions between all entities by beginning with a dense topology. Additionally, the overhead on the relation prediction model is huge since the number of pairwise comparison can grow non-linearly with the number of detected objects. We make three key contributions. First, we tackle the problem of scene graph generation with a graph generative approach without constructing expensive pairwise comparisons. Second, we propose the idea of iterative interaction graph generation and global contextualized relational reasoning using a two-stage transformer-based architecture. Lastly, we show that the proposed approach achieves state-of-the-art performance across all three scene graph generation tasks while considering only 20% of all possible pairwise edges. So how do we do it? At first, we ground the concept of an input image using a first error in an object detector. We have the labels and the features of the nodes or objects from this stage. In the second step, we perform structural reasoning over this node and sample the graph. We use a generative graph transformer which iteratively updates the adjacency matrix between the nodes. After we have a sample graph, we take the adjacency matrix or the defined edge list as an input to the third step of our approach, relational reasoning. We incorporate the global features of the input image as well as the visual and semantic features of the node. After the relation predictions, we form the scene graph using the usual way with confidence scores of predicates, objects, as well as the confidence of being a meaningful edge from the structural reasoning. At the heart of our approach is graph sampling. We find the sample graph structure using a graph generative transformer. Here is how the algorithm works. We take a list of nodes with labels, visual features, and bounding box information for each node as an input to the algorithm. The output is a sample graph with a list of nodes and edges in the form of an adjacency matrix. In the beginning, we initialize an empty graph, an empty adjacency matrix, and an empty edge list. Once we have that, we iterate over all the nodes in the node list and find a context vector conditioning on each of the node's features, previously decoded adjacency matrix up to the current step, and hypothesized labels. After adding a positional encoding, we project the context vector to a linear space and decode it by a transformer decoder and find the adjacency list of the current node. We iteratively update the adjacency matrix and the edge list with each node looking through the node list. We evaluate our approach using the Stanford split of visual genome dataset containing 108K images with 150 object classes sharing 50 types of relationships. We use the standard predicate classification, scene graph classification, and scene graph generation tasks to evaluate our approach. In our work, we report our results using mean recall metric. Here, we compare our model with the state of the art. Note that we do not use any unbiasing techniques to tackle the long tail distribution of the visual genome predicate label. As you can see, our approach IS-GGT outperforms all models that do not use unbiasing. We also outperform some early unbiasing models across all three tasks. We achieve competitive performance to current state-of-the-art unbiasing models. The approaches that outperform our approach are underlined in the table. We calculated the zero-shot recall values with graph constraints to see how well our approach generalizes to unseen edge triplets. As seen in the table, we outperform all models that have reported zero-shot evaluation. Since our approach relies on graph sampling, we performed ablation studies to see how graph sampling impacts the overall performance. Considering only 20% of the number of total possible edges, we outperform most of the existing methods that do not use any unbiasing and in some models with unbiasing. Here, we show some qualitative results obtained from our approach. The predicate in the red are the zero-shot relations which the model did not see in the training. We also detect many relations which are not present in the ground truth but are semantically meaningful. We have provided more qualitative results in our project page. Please feel free to scan the QR code from here and check out our project page for more details. Please come visit us at our poster at Tuesday afternoon session. Thank you.